Hello everyone, welcome to this another instructional video. This presentation is related to the concept light geometric optics. And the title of this presentation is Total Internal Reflection. In this presentation, we are going to look into the physics behind this phenomenon, total internal reflection of light. This will be the outline for this presentation. First, we are going to discuss about the criteria for total internal reflection. Means that we are going to look into the conditions as to how this phenomenon will going to occur. Second, we are going to define the critical angle and relate this concept to the concept that we have covered before, the concept of refractive index. And then after that, we are going to enumerate examples of total internal reflection of light that we observe in our surrounding. Before we dive into our formal discussion on the concept of total internal reflection of light, let us first build our understanding on this concept using this simple demonstration. The title of this demonstration is Disappearing Pencil. So what you are going to do with this is that you are going to insert a pencil into an empty test tube as shown in this diagram right here. Now you put the test tube in a container and you fill with water that container as shown in this diagram too. Now notice that our pencil disappear with respect to what we had a while ago. But if you add water into the test tube, these pencil will going to reappear again. To see this demonstration in action, I want you to watch this video clip, Disappearing Pencil.
A test tube is placed in a beaker. Insert a pencil into the test tube. Why does the pencil disappear when water is poured into the beaker? Why does the pencil reappear when water is poured into the test tube?
For us to develop a conceptual understanding as to how we can explain that kind of phenomenon as shown on that video clip, let us build our conceptual understanding on this concept, total internal reflection. In order for us to do that, let us have this experimental setup. You can perform this experiment inside the laboratory, and this experiment would give us a good idea of what total internal reflection is. The procedure will be the following. You need to secure the necessary materials for this experiment. First, you need to have a semicircular glass block, and you have a circular protractor, and you need to have also a ray of light or a source of light. Now you are going to direct a ray of light to enter the semicircular glass block from its curved edge towards its center O, as shown in this diagram here. Now, you're going to slowly increase the angle of the incidence, this theta g, and watch how the refracted ray changes. To see exactly how we can do this experiment in the laboratory, I want you to watch this video presentation.
Direct a ray of light to enter the semicircular glass block from its curved edge towards its center. Move the ray box slowly to increase the angle of incidence in the glass block. When the refracted ray becomes almost parallel to the straight edge of the glass block, record the angle of incidence. This angle is known as the critical angle of glass. What is the critical angle of the glass block used in this video?
We are now in section 1, criteria for total internal reflection. Now, from that video clip, you saw that there are three rays hitting the inside face of a semicircular glass block at different angles. And these rays are the following: the incident ray, reflected ray, and the refracted ray. The incident ray is the light ray coming from the source of light. Now, this incident ray splits into two rays: a reflected ray inside the glass, as shown in the diagram here, and a refracted ray as shown in this diagram also. Note that the incident ray also splits into two rays when the angle of refraction is around 90 degrees, as shown in this diagram right here. As the refracted ray just manages to leave the glass surface, our incident ray is now going to experience total internal reflection inside the glass. Here, there is no refracted ray present. Let us then define critical angle. So critical angle, class, is simply the angle of incidence at which the angle of refraction is equal to 90 degrees. So you can see here, this is our critical angle, C, okay? And you have this refracted ray, the angle of refraction is around 90 degrees. If the angle of incidence, okay, the angle of incidence right here with respect to the normal is greater than the C, or the critical angle, the light ray will be totally reflected inside the glass block. Then the surface of this glass block will act like a mirror, and the total internal reflection, class, will occur. Note that total internal reflection, class, only happen or only occurs for an incident ray in an optically denser medium. What does it mean when you say optically denser medium? It means that having a higher refractive index. It does not occur when light passes from an optically less dense medium to an optically denser medium, no matter how large is the angle of incidence. To fully understand what I am saying here, I want you to watch this video clip, Total Internal Reflection in Water.
Partly fill the container with colored water. Then inject some smoke above the water. Direct a laser beam to the water from below. Notice how the beam refracts when it enters air from the water. What happens to the refracted ray when the angle of incidence is gradually increased?
We are now in section 2, critical angle and refractive index. In this section, we are going to derive the equation for critical angle and relate this concept to the concept of refractive index. In our previous discussion, we found out what is a critical angle. As we all know, this is the angle of incidence in a medium, which is equal to C when the angle of refraction in air is equal to 90 degrees. Now, using the concept of Snell's law, N is equal to sine, which is now the angle of incidence in terms of critical angle, will be equal to the refractive index of air multiplied by sine 90 degrees. We be able to determine the quantity refractive index in terms of the critical angle. So n is equal to 1 over sine c. Now the critical angle will be expressed as the sine inverse of 1 over n. Let us remember that n is the refractive index of the medium. In this figure, you will see how the reflected and refracted ray change in terms of its brightness once it is projected at a given angle. You can see as you gradually increase the angle of incidence, the refracted ray is now getting dimmer and dimmer until such time that you will hit the critical angle where your refracted ray is 90 degrees After that, there will be a total internal reflection. Let us have an example to further deepen our understanding of critical angle and refractive index. Finding the path of a light ray. A light ray traveling in the direction EO in air enters a rectangular glass block as shown in this diagram right here. The angle of incidence is equal to 30 degrees, located here, and the angle of refraction is 18 degrees as it is located here. Letter A question says find the refractive index N of the glass block. To find that, all we have to do is to use the concept of Snell's law. Using Snell's law, we be able to calculate the refractive index of this glass block. And that is equal to sine 30 over sine 18 degrees is equal to 1.62. Now, the refractive index is equal to 1.62. Letter B question says that you need to determine the critical angle C for the glass-air interface. So our glass-air interface critical angle can be calculated using this equation that the critical angle is equal to the sine inverse of 1 over n. And we know what is our n, that is equal to 1.62. Therefore, our critical angle using this equation will be equal to 38.1 degrees. Letter C question. If the ray is incident on the surface BC, from which surface and at what angle will it leave the block? So from this diagram, we'll be able to calculate the angle of refraction here. So from here, we now be able to calculate exactly as to where it comes out. The ray comes out from surface AD. The emergent angle from the normal is equal to 60 degrees. To further elaborate the concept of total internal reflection of light, I want you to watch this video, this appearing button.
The button is placed under a beaker. Why does the button disappear when water is poured into the beaker? Why does the button reappear when there is water underneath the beaker?
Furthermore, I want you to watch also this video, The Magic Cube.
This is a photo stand. It consists of 3 plates. We can see that there is a photo on each plate from this direction. This cube is a magic cube. If we place it onto the photo stand, we will find something interesting happens. Look, the photo stand looks very different now. We can only see one kind of photo from each face of the cube. Actually, this magic cube is just a simple glass cube. Do you know the principle behind it?
Section 3. Examples of total internal reflection. In this section class, I will be discussing to you examples of those materials or phenomena where the concept of total internal reflection of light is being applied. First example is the optical fiber. A light ray can pass along a glass fiber from one end to the other. The fiber guides light by a series of total internal reflections. Light then bounces along the inner walls of that optical fiber. Well, to understand what I am talking here, I want you to watch this video clip entitled Simple Optical Fiber.
Do you know what this is? Do you think that it's a fishing line? Indeed, this is a simple optical fibre. It is made of a plastic core with no outer cladding. A ray of light is incident from air on the end of the fibre at an angle. What can you see at the other end of the fibre? We can use a perspex rod to show how light turns. A ray of light is incident from air on the end of a bent perspex rod at an angle. We can see a ray of light undergoing a series of internal reflections along the inner walls of the bent perspex rod from one end to the other. Some ornaments make use of the same working principle to produce such a beautiful effect. Can you think of other applications of optical fiber?
Similarly, total internal reflection of light can also occur in water at similar characteristics as to the optical fiber. And I want you to watch this another video clip, Water Light Guide.
Switch on the waterproof torch and put it into the bucket. Then remove the plasticine. What can you observe when a jet of water is flowing out from the bucket?
So what is exactly an optical fiber? Well, an optical fiber is made of very pure glass. Also, it is very thin. At the same time, it is flexible. By the way, an optical fiber is widely used in telecommunications, just like it is used for transmitting information in the internet or used in telephone lines. Flashes of light from a laser send signals at a high speed can only be possible through the use of optical fiber. Optical fiber also can be used as light guides for doctors to see inside a human body. And that is what we call endoscopy. Well, to see how doctors make use of these optical fiber in terms of diagnosing diseases, I want you to watch this video clip entitled Endoscope.
An endoscope consists of an optical fiber cable with a small light source and a video camera at one end. The cable is flexible and can be inserted into the human body to enable the doctor to examine internal organs. The endoscope is inserted through the mouth into the patient's stomach. It first passes through the throat and the esophagus. The endoscope then enters the stomach. It can be bent to examine different parts of the stomach. A cable with a hook at one end can be inserted through the endoscope into the stomach to take samples of the bad tissues of an ulcer for examination.
Let us extend our understanding on optical fibers through this example. A simple optical fiber is made of a plastic core with no outer cladding. The refractive index of the plastic is 1.6. A ray of light is incident from air on one end of the fiber at an angle of 60 degrees. So you can see from this diagram, this is our optical fiber, and you have the angle of incidence, which is 60 degrees. You have this alpha, you have this beta. And the refractive index is equal to 1.6. Letter A question. You calculate the alpha and the beta. By employing Snell's law, we can calculate our alpha, and our alpha is equal to 32.8 degrees. Now, calculating our beta, we can calculate it using this relationship, 90 degrees minus alpha, where our alpha is 32.8, therefore the beta will now be equal to 57.2 degrees. Question letter B. You calculate the critical angle for the core-air interface. Is the ray totally reflected inside the core? Okay, so to calculate the critical angle, Let us use the critical angle formula, and that is equal to sine inverse 1 over n, and n is equal to 1.6, and therefore the critical angle is equal to 38.7 degrees. Since beta is greater than c from the calculation letter A, therefore the ray is totally reflected inside the core. Question letter C. If the core is coated with cladding that has a refractive index n, which is equal to 1.1, what will be the critical angle of the core cladding interface? Okay, so to calculate, again, we can employ the concept of Snell's law, and from that, we can determine the critical angle, and that is equal to 43.4 degrees. Moving on to our second example of total internal reflection, using prisms as mirrors. A plane mirror class consists of a glass sheet coating and a reflective material, also known as silvering, that is covered on the back surface of the glass. Now, if you have a multiple reflections between the front and the back surface, these would form a fainter images as to I1 and I2 on the diagram. Okay, so you can see from this diagram right here, this is your I1 and your I2. Now, making the main image, which is your I2 right here, so this is the image, less clear. Similarly, a prism works like a mirror. If light rays are incident on its inside face at an angle greater than C. Now, prism class do not form multiple images. We use prism in many optical instruments for quality images, like for example, cameras, periscope, and binoculars. Here is an example of that one, and we call this one pentaprism because there are around 5 sides of this prism. Also, prisms can be found in headlights reflectors in cars and cat's eyes on the road. So what is a cat's eye? This is exactly a cat's eye. These are reflectors on the road, and also you have a reflector on a car. So basically, prisms make use of the principle of total internal reflection, as shown in this diagram right here. Like for example, this cat's eye, you have a light ray, incident light ray, traveling into that reflector, and inside of that reflector there is a total internal reflection happening, and you can see exactly the reflected light. Moving on to the third example, we have mirage. On a hot day, sometimes the road at a distance ahead appears wet and reflective. As you can see from this diagram right here, this is the runway of the airport, and you can see a reflection of the sky. Similarly, this is a ground surface where you can see also the reflection of the mountains. The reflection of the sky can be seen during hot days in a dry surface. Well, this phenomenon is known as mirage. This occurrence is common in a desert area. To picture out what a mirage is, I want you to watch these video clips, mirage in a water tank and mirage at the airport.
A laser pointer directs a ray of light into a tank of water from the side. The ray is totally internally reflected at the water surface. Some concentrated sugar solution is now added to the bottom of the tank of water. After some time, the ray of light is totally internally reflected in the sugar solution, and the ray is curved rather than straight. Why is this so? This is the old Hong Kong Kai Tak Airport. An aeroplane is landing. Can you see the image beneath the aeroplane? This is a mirage. Watch this again.
To describe what mirage is, this is exactly the explanation to that. If you have an air that is near the ground, it means that this air is hot, at the same time will have a lower refractive index. When the light from the sky is gradually refracted more toward the horizontal, as shown from this diagram right here, total internal reflection will happen. Okay, so total internal reflection will happen due to the fact that here, the refractive index in this area is different compared to the refractive index of the air in this area. As a consequence, you will be able to see the image of the sky when you look down because there is a total internal reflection happening here, and this is exactly what you will see through your naked eye. To deepen our knowledge about total internal reflection, let us have this example number 3 entitled Super Mirage. In a special case of mirage, commonly known as superior mirage, an observer may see an inverted island that floats in the sky. Such a mirage appears when the temperature of the air increases with height. This is most likely to form when the sea is much colder than the atmosphere. The air near the sea surface has a higher refractive index. Light traveling upwards is gradually refracted but in the opposite way from an ordinary mirage. This is why we see the illusion in the sky instead of on the ground. Okay, question. How does the refractive index of air vary with height when a superior mirage is formed? Well, the answer is straightforward. The refractive index of the air decreases as height increases. Question letter B. Explain how the inverted image of the island can be formed in this way. And this will be the explanation. The refractive index of the air will going to decrease. Therefore, the light from the island is gradually refracted more and more towards the horizontal. As a consequence, the light meets the air at an angle greater than the critical angle C. Well, because of that, total internal reflection then occurs. As a consequence, the light then travels downward. You will see then the image of the island in the mid-air. Now, letter C, sketch a ray diagram to show how the superior mirage is formed. Mark the positions of the object and the image. To draw or sketch the diagram, it will be shown as this. Moving on to our fourth example of total internal reflection, and that is diamonds. Diamonds glass has large refractive index, therefore it is easily to reflect light which goes into them. Thus, it has a sparkling effect as to how we see a diamond. People who are making jewelries should make sure that the facets of that diamond have to be cut at a carefully chosen angles, or light may escape through the bottom or side of it. As a result, the diamond will not show a sparkling effect. Let us have an example in relation to this concept. Example number 4. Diamond and glass jewelry. We have the following known quantities. The refractive index of diamond is equal to 2.42 and the refractive index of glass is equal to 1.50. Letter A. Find the critical angles for a diamond-air interface and a glass-air interface. So to calculate the critical angle, we have the following solution. For diamond, the critical angle is equal to sine inverse of 1 divided by 2.42, and the angle is equal to 24.4. While for glass, the critical angle is equal to the sine inverse of 1 over 1.50, and the critical angle is equal to 41.8. Question letter B. Can glass jewelry be cut to give similar brilliance to that of a diamond? Why? The critical angle for a glass-air interface is much larger. Therefore, a much smaller amount of light going into glass jewelry is totally internally reflected. As a consequence, it does not have the same brilliance as diamond jewelry. Moving to the next example, fish eye view. This will be the last example for phenomenon that make use of the concept of total internal reflection of light. What is a fish eye view all about? A fish or a diver underwater can see everything above the water surface, but the view is squeezed into a cone with an angle of approximately around 98 degrees. As shown in this diagram here, you can see that you have this cone of view which has a total angle of 98 degrees approximately, and on the side outside of the cone the light rays will going to experience total internal reflection. Thus, inside the water surface it will become a mirror. To understand what I am saying here, I want you to watch this video clip about total internal reflection in a fish tank.
This water tank filled with colorized water is used to demonstrate the fisheye view. Put a flashlight into the tank and illuminate the water from below. How does the light refract when it enters the air from the water at different angles?
To elaborate further our understanding on fish eye view, let us have this example number 5, diameter of diver's view. A diver who looks upward is 0.5 meters below the surface relative to its eyes, and we have the refractive index of the water which is 1.33. Now, the question is, what will be the angle of the fish eye view he sees? So to calculate that, again, we can use the concept that we already covered a while ago, using the principle of the critical angle. Our critical angle, as you can see from this diagram right here, relative to the 90 degrees of the refracted ray. So remember, our diver is 0.5 meters relative to its eye and to the surface. So our critical angle is located somewhere here. So to calculate the critical angle, we use the critical angle formula, which is equal to sine inverse 1 over n. Now, our n is the refractive index of water, that is 1.33. Therefore, our critical angle will be around 48.8 degrees. Now, since we want to determine what is the angle of fish eye view, that critical angle is equivalent to our theta right here. So therefore, the angle of the fish eye view will be twice of that theta, which is twice of the critical angle. Therefore, it will be equal to 97.6, of which, according to our discussion a while ago, the fish eye view would approximately have an angle of 98 degrees. Question letter B. What will be the diameter of the diver's view? So the diameter of the diver's view is simply equal to 2 times the radius of the cone. And that is around 2 times 0.5 times tangent theta. So our diameter is around 1.14 meter. Okay, that's the end of this presentation. I hope you've learned something about the concept of total internal reflection. Thank you for watching. Have a nice day.